Hi, welcome everybody. In this video, we will construct a Bootstrap distribution for a proportion in R. And so we'll be working with this Colab notebook, and the Colab notebook is running R, and you can get a link to this notebook in the description down below. And the data that we're going to be working with is a data frame called environmental, which is in a package called lattice. And this contains various observations taken in New York City. The source for the data is below, and you can always run a question mark environmental to look into the help manual for this data. So I want to focus this video on constructing the Bootstrap proportion and not get into the details about behind the data, though that's certainly interesting. So this code cell below, we're going to just load the lattice package, summarize the environmental data frame as a whole, and then extract one of the variables from that data frame. So you can see there are 4 different variables in the environmental data frame. The one that we're going to be working with is the variable ozone. So this command is going to extract that variable and just store it in this vector that we're calling NYC.ozone. And we're going to be bootstrapping from this sample. And what's really important when we're bootstrapping is to consider, well, how many observations are in the data set, since each of our bootstrap resamples is going to need to contain the same number of observations as our sample. So that's what's being asked in question 1A. So in order to calculate the size of our sample, we can run a length command, for example, and we can run length, and our vector is New York City.oz. And here we can see there are 111 observations in our original sample, which is New York City ozone observations. So based on this sample, if we wanted to come up with an estimate for the mean concentration, ozone concentration in New York City over all days and times, we just have a sample of 111 observations. So from that sample, we can think about different estimators that might be reasonable. We can use a mean or a median or a trimmed mean, or there might be other estimators that might make sense to use. We'll use the most obvious one, perhaps, which is we'll use the mean of the sample as an estimate for the mean of the population. So the sample mean would just be the mean New York City NYC.oz. And here we can see that from our sample, the mean ozone concentration is 42 parts per billion. And this gives us a good estimate, a good starting point for our estimate for the population mean mu. We can approximate that the ozone concentration for all days and times in New York City, therefore, a reasonable estimate would be the sample mean, which is 42.00099 parts per billion. And I realize I forgot to create a plot in the first question, part A. So before moving on, let's just take a look at a histogram, for example, of the full sample, which is 111 observations. And you can see the mean 42 is over here, and this data is heavily skewed to the right. We have a big tail to the right. And so this video, we're going to take a look at a bootstrap distribution for a proportion. And the variable that we're working with, ozone, is a quantitative variable. So although this is a quantitative variable where we typically might summarize the data with things like means and mediances and variance, there still might be occasions where it's appropriate to use a proportion as a summary for a quantitative variable. So for example, we can consider what proportion of the observations in our sample have a ozone concentration that exceeds the standards. And we're going to be working with the standards of 70 parts per billion is what's considered a high ozone concentration. So overall, the mean of the data is 42, it's low. That doesn't mean that there aren't times where we should be concerned about a high ozone concentration. You can see from the plot above, there were plenty of observations that were above this high threshold, this high standard. So we can consider instead asking what proportion of observations in this sample have of all time in New York City is the ozone concentration high. Here, we're going to run this first code cell. And what this code cell is going to do, the output here is just picking off the first 30 observations in this vector New York City ozone concentration. So the first observation, 41, corresponds to an observation where the ozone concentration was 41 parts per billion. Here's the next observation was 36, and so on. And one way that we can convert this quantitative variable to categorical data in a meaningful way is using a logical test, such as, is the observation greater than 70? So that logical test would look like NYC.OZ greater than 70. And so that's going to look at each individual entry in the vector NYC.OZ, and it's going to say, is that entry bigger than 70? If so, it's going to assign it a 1. If not, it's going to assign it a 0. And so looking at these first 30 observations out of the total 111 that we have in this sample, they're pretty much all zeros. We have a 1 over here at 115. We have a 1 over here at 71. And all of the rest of the values that we're displaying here would get assigned to 0. And so now this quantitative data is mapped to a vector of zeros and ones. So we can think of this as two categories. Category 0 means no, the value is not bigger than 70. Category 1 means yes, the observation is bigger than 70. And then down here, we can run the sum NYC.OZ greater than 70. And this is going to do two operations at once. It's going to do the conversion that we have above into this vector of zeros and ones, and then it's going to add up all of those values, which in essence is going to count up how many observations in our sample are bigger than 70. We can see from this output that 24 out of the 111 have ozone concentration that was bigger than 70. And so if the question is, well, what proportion of all time in New York City is the ozone concentration greater than 70 parts per billion, a good starting point for an estimate would be to take this sample and say, based on this sample, 24 out of 111, which is about 21.62%, seems to be a good estimate. And we denote this sample with a p hat for a sample proportion. And we can do this all at once in R with a couple of different methods. And so one method that we can do is count up, just as we did before, how many observations in the data set are bigger than 70, and then divide that by the sample proportion. So here, I'm just counting up that there are how many observations in the New York's NYC.OZ vector. And then we're going to count up how many observations were bigger than 70. That's the 24. We take the 24 divided by the 111, and that just matches the proportion that we have up above. A more concise method for doing this, which is great when you're running for loops, is to run code that is more concise, is to use the mean command down below. And so this does the same exact operation as the method above. This is going to count up how many observations are bigger than 70 and then divide it by the sample size, which is 111. So here we could calculate the sample mean using either of these methods. And down the line, you might want to store this value to something like p hat if you want to use this in code down the line. So either method that we're using, we're getting a sample proportion from this sample of 111 values that our sample proportion was 0.2612. And if our goal is to approximate what proportion of all time in New York City is the ozone concentration greater than 70 parts per billion, we wouldn't want to state that it's exactly this, because if we pick a different sample, we're likely to get a slightly different sample proportion. So how much uncertainty should we build into our estimate? And as we've seen, sampling distributions, and in particular, the standard error of sampling distributions, that's a great way to build in some uncertainty into our estimates. So the next question is going to take us through the process of creating a bootstrap distribution for a sample proportion. And again, the proportion that we're going to be looking at is, well, what proportion of observations have an ozone concentration greater than 70 parts per billion. So in the for loop that we're going to run below, there are really two main things that we're going to need to do. The first is pick a bootstrap resample from our original sample, and then secondly, calculate a proportion from that sample. So in the first line below, we're going to create 10 to the fifth, so like 100,000 different bootstrap resamples. And each sample proportion we're going to store in this numeric vector that we're calling bootprop. And so our for loop is going to run 10 to the fifth times. And each time we want to jump in and create a bootstrap resample that we're calling X. And so that sample is going to be created from the vector NYC.OZ. We want it to have the same size as the original sample. So for clarity, I'm going to calculate that as length NYC.OZ, so it's clear what value this is. But in practice, you probably would want to run this outside of the loop, store this value, and then inside the loop, just use this stored value so that you can save some time calculating this. But it's not going to have an effect on this code. Won't take long to run. And so for clarity, I'm just going to leave the size as the function that's calculating how many observations are in NYC.OZ. And with bootstrapping, we always want to sample with replacement. And then the statistic that we're going to calculate is going to be the sample, the proportion of the sample that has ozone concentration greater than 70 parts per billion. So in this case, we can do that just by the method that we described above, which is to apply a logical test. But now we're going to apply that test to the bootstrap resample, which is X. I want to calculate how many observations in my bootstrap resample are greater than 70. And the mean is going to count up how many there are and then divide by the size of that bootstrap resample. So the first step is calculating my bootstrap resample. The second step in this for loop is calculating my sample proportion. And then down below, we're going to create a histogram to display these observations. And we're going to mark a couple of important values on that histogram. So you can see this took a couple seconds to run, maybe 1 second to run. And here's our bootstrap distribution for the sample proportion. Each of these proportions is corresponding to what proportion of observations had a high ozone concentration, greater than 70 parts per billion. And so the line in red, that corresponds to the sample proportion of our observed data, which was being stored in NYC.OZ. So this is our observed sample. And the line in blue might be the bootstrap estimate for the population parameter. So here we're calculating the mean of the bootstrap distribution for the proportion. So we might use the mean of many bootstrap proportions as an estimate for the population proportion. So here we're just comparing them visually, and we certainly could calculate them separately and compare those values. So down below, this is asking us to calculate the bootstrap bias for using the bootstrap distribution to estimate the population proportion. So there are two things that are going to go into this equation. One is, what is our estimator? And here we're going to use the mean of the bootstrap distribution, which we call boot prop. So this is our estimator. And we're going to compare that to the sample proportion, which again was NYC.OZ. dot OZ, we're going to calculate how many observations in that sample were bigger than 70, and then take the mean of that, which is our sample proportion. And the bootstrap bias is going to be the difference in these two values. So I'm going to take my bootstrap estimate, and I'm going to subtract from that our sample proportion. And we can see here, those are the two separate components. And then the bias would be the difference of those two, which winds up being 5.7 times 10 to the minus fifth. So this is basically 0. So this is telling me that our bootstrap estimate for the population proportion does not have a lot of bias. But we should keep in mind here that we are estimating a proportion, and proportions are values between 0 and 1. So these are not large values to begin with, so we shouldn't expect a whole lot of spread in those values. So sometimes just looking at the bias might not be the be-all, tell-all, but we might want to think about, well, how much bias is there relative to the spread of values that we're getting in our bootstrap distribution? So the bootstrap standard error is going to be useful to compare, relatively speaking, is this a lot of bias? And to calculate the standard error for the bootstrap distribution, the standard error is just the standard deviation of a sampling distribution. So in this case, the sampling distribution is the bootstrap distribution for the proportion, which we stored in bootprop. And you can see here that the standard error that we're getting for the bootstrap distribution is 0.039. And these values are going to vary a little bit. If you're running this code yourself, you might get slightly different values just because we are approximating the bootstrap distribution by generating 10 to the fifth possible bootstrap resamples and not necessarily generating all of them. So there's going to be some minor variability in the output, but it should be pretty close to what I'm getting.